and welcome back to another video on my channel. Today we will be talking about the Simpson line theorem, and just to mention again, I haven't been posting in a little bit, so to make up for it, I will release 5 videos this week, and this is the third of them. The first video was the last video in our Intro to Calculus series, and the last one, the one right before this one, and 2 after this, will be the 4 final videos of advanced trigonometry / geometry, and then we will move on to our actual calculus series. I cannot wait for that because I really enjoy calculus and I find that it actually ties a lot of things together. So without further ado, let's move on to the actual presentation. Today we're going to discover a very beautiful geometric theorem, the story behind its name, how to prove it, and why it matters. How to prove it and the theorem itself, this is stuff we have been covering, same with why it matters in mathematics. But the story behind its name, this one, I actually think it's very interesting, and I actually want to say a few things about that too. So, this is the theorem. Take any triangle, and then its circumcircle, where there is a circle through all vertices. Then there is a point P on the circle, a circumcircle, or circle. That is not A, B, or C. Then in the visual, E will be X in the proof, F will be Y, and D will be Z. We will come back to this. But the main theorem is D, E, and F form a straight line. And these 3 points are, if we take the line from A to B and extend it outwards until we find the closest point to P, and do that for the other lines. So D is the closest point to P, E is the closest point to P on this line, and F is the closest point to P for AC. These 3 points are collinear, or they will form one straight line. A step-by-step construction is pretty simple. We just draw perpendiculars from P to each side and then mark the feet of the perpendiculars as X, Y, Z. As I said earlier, when I was looking at the image, as I said above and in the image slide, when I found the image, it was D, E, and F, but I had already labeled everything as X, Y, and Z, so I decided to just change it for the proof, as I couldn't really find anything that satisfied the image for X, Y, and Z. So that's why everything is there above, and that's why I'm saying mark the feet of the perpendiculars as X, Y, and Z. Also, yes, they are perpendicular, but they're also the closest point to each. And the question is really what's special about these 3 points, and that's what the theorem is, or the line. That, yes, all 3 of these points will lie on the same line, and if you didn't know already, or if you haven't guessed, this is known as Simsons line. Now, of course, these 3 feet are always familiar, and when I see this visual over here, to remind myself to go up here, setting the stage. This is the line in pink over here. D, E, and F, all of these are perpendicular and the closest from each point. So that's basically what it is. All 3 of these lie on the same line, and it's Simpson's line. And then an emphasis, this works for any point on the circumcircle. So let's move P. Let's say if we move it over here and we draw perpendiculars to everything where my cursor is, and then we draw perpendicular over here, perpendicular over here, everything everywhere, it will also form a line. Now if we take every Simpson line and then look at the rough shape, it in fact, as you go through every point on the circle, it's just a lot of lines outside and like a filling, but there is actually a shape called a deltoid, which is something with 3 curves, or a triangle with 3 curves instead of just 3 straight lines. The formal theorem statement is if and only if those 3 points are collinear, then P is on the circumcircle. Now, the reason it's the opposite is that is the theorem of Simpson's line, but not the actual Simpson line itself. And today we're going to be proving how the Simpson line works, and not exactly the theorem, because if you could just work backwards from the proof that I'm giving you today to figure out the Simpson line theorem that P is on the circumcircle. And then over here, if x, y, and z are feet of perpendiculars from P to sides BC, AC, AB respectively, then x, y, z are collinear if and only if P lies on the circumcircle of triangle ABC. So that's the mathematical notation and almost like the backstory that all of the other x, y, and z are feet of the perpendiculars here and there, and basically replaces the setting the stage slide that was above. Now this is probably my favorite slide in this entire presentation and probably the part that I want to talk about the most. While it might not be the longest section, this is one of my favorite sections and it highlights something that is still prevalent all around the world. Then the name is actually, it's called Simson line, but Robert Simson, 1867 to 1768, never actually studied this line. He studied other aspects of Euclidean geometry, or Euclidean geometry. Anyone in the comments, please make sure to correct me because I think I butchered that pronunciation. Now, the truth is, William Wallace, 1768 to 1843, who was actually born on the year of Robert Simson's death, discovered it in 1799. So sometimes it's called the Wallace-Simpson theorem or the Wallace-Simpson line. And the biggest lesson over here is a mathematical attribution isn't always accurate and it's still there all around the world. In fact, the Indians and the Arabs actually knew the quadratic formula a long time ago, but it's actually still called the quadratic formula, especially for many theorems discovered before the Renaissance period or before many of the mathematicians we know today, like Isaac Newton, Gauss, Frederick Gauss, Riemann, and others. Normally they have their own theorems, which are normally pretty advanced and weren't known by ancient civilizations, but it still doesn't disprove the case that a lot of math is incorrectly attributed. In fact, ancient India had the entire base 10 number system, but most people only attributed to have discovered 0. So I just wanted to tell you that because not everything is accurate. If you really want to know, you should look deep and do your own research instead of just looking at the name of the theorem. So that's all the historical mystery. Let's move on to the proof. This is just a small connection over here. The general case is actually these perpendicular feet usually form a triangle if P is anywhere else. But if P is on the circumcircle, the triangle collapses and becomes a line instead of a full triangle. There are 4 main proof approaches. There's angle chasing, coordinate geometry, parallel line construction, and Menelaus' theorem application. We will actually be talking about Menelaus' theorem in the next video. But today's focus is using angle chasing, basically using circle properties and other angle properties. This is the foundation of the proof setup. Basically, right angles create cyclic quadrilaterals, and if opposite angles in a quadrilateral sum to 180 degrees, it's a cyclic quadrilateral. And same goes for the opposite. So if it's a cyclic quadrilateral, we can say that the angles over there are sum up to 180 degrees. So we have 3 cyclic quadrilaterals, BXPZ, CXPY, and AYPZ. So first we have PXB is equal to PZB is equal to PZP is equal to 90 degrees because that's the perpendicular angle, and that shows that PXB plus PCB is equal to 180 degrees, and that proves that this is a cyclic quadrilateral. The same thing goes for CXPY and AYPZ. Now, one of the main essential tools that we're going to be using is the inscribed angle theorem, and this theorem says that inscribed angles subtending the same arc are equal. Why this matters is it gives us angle relationships within each cyclic quadrilateral. This is our first step of the proof, inscribed angles in cyclic quadrilaterals. The strategy is we'll use these cyclic quadrilaterals to establish angle equalities, then show these equalities force collinearity due to a very beautiful geometric construction. So, apply inscribed angle theorem to each quadrilateral. So, So our few angles that we're going to figure out are equal to is the first and second cyclic quadrilateral, BXPZ and CXPY. This means XZP is equal to XBP, both subtend the same arc on the circumcircle of BXPZ. And if you are unfamiliar with these theorems, you can look at my advanced trigonometry/geometry series before this, or you can look at my regular geometry series where I cover a lot of proofs and theorems used in many geometry problems. And for the next one, it's XYP is equal to XCP. Both subintend arc, the same arc on the circle of CXPY. Key points, these angles kind of look at the same arc from different points on the circle, and that's why they're equal. And remember, this is basically a theorem, and if you want to know the theorem I said, you can always look at my geometry series, or if you want to know any other theorems, most of them won't be used here. Actually, all of them won't be used here. It's just basic geometry theorems proving this. But in general, if you want to check out my other videos, you can also check out my Intro to Calculus series and my Advanced Trigonometry/Geometry series, which this is a part of. But these are just the last 4 videos. I decided to take a break from the Advanced Geometry/Trigonometry series as I wanted to do something new. So, what we've established is 2 very important angle inequalities from cyclic quadrilaterals, and now we need to connect these separate relationships, which brings us on to step 2. There is one very key fact. P is on the triangle circumcircle. The game changer is, since P lies on the circumcircle of the triangle ABC, XBP is equal to XCP. Inscribed angles subtending the same arc on the main circumcircle. Now, if you ever have a question about the visuals, you can always look up to our setting the stage slide. You can pause my video, go back to see what I'm talking about all the way over here. And why does this even matter? Okay, yeah, we have inscribed angle theorem, and yeah, P is on the circumcircle. That was given. But this connects the angles from our 2 different cyclic quadrilaterals, and without P being on the circumcircle, this equality wouldn't hold, and it would be a triangle instead of a line. And this is basically the heart or the main thing about why this theorem works. Our third step of the proof is chaining the angle equalities. So XZP is equal to XBP, XYP is equal to XCP, those are from step 1, and XBP is equal to XCP, so that means XZP is equal to XYP. And this is just the basic mathematical logic behind it, and it is the transitive property of equality in action. The final step of the proof involves making these equal angles become collinearity. So the geometric insight is both of these angles are from point P to point X. If these angles are equal, then that means the rays PZ and PY make equal angles with the ray X. And due to geometric construction, this forces the points to lie on a straight line. And of course, if you're confused with the visuals and how it works, you can always look online. There's many people who will show you the visual. I'm trying to show you the main math behind it, the mathematical rigor behind it. But of course, there are many more channels on YouTube, and I definitely recommend looking out for them to see the visual explanation of that as well. Now, right angles become cyclic quadrilaterals, angle inequalities. P on circumcircle is the biggest inequality, chain of inequalities, and equal angles from P. This is basically the gist of it and the complete logic of the proof. We've done it! We've proven the Simpson line, or the Wallace-Simpson line as it should really be said. But there are other ways to prove the Simpson line theorem. We could use coordinate geometry. So we place a triangle in a coordinate system, find the equations for the perpendiculars and their feet, and show algebraically that the feet satisfy a linear equation. Another one is parallel line constructions. We could construct parallel lines, auxiliary parallel lines, use properties of parallel lines and similar triangles, and then demonstrate that parallelism forces collinearity. The final method is Menelaus's theorem. This uses ratios and cross ratios on triangle sides And this is the theorem we will be covering in the 4th video of the 5 videos that I'm releasing this week. And this shows the ratio conditions are satisfied. Why multiple proofs matter. This shows the theorem's deep connections across geometry and demonstrates different mathematical thinking approaches and provides multiple ways to understand the same truth and connects areas from all across geometry, kind of leading to a point that everything is connected even if you don't think it is. Thank you so much for watching to the end of this video. I really hope you have a good day and I hope you learned something from this. There are many lessons to be taught from this, and I hope this still keeps your curiosity about math alive, and I hope that you watch some more of my videos, you like, you subscribe, you hit that notification button. It really helps out a ton, and it shows me, it gives me confidence boost and shows me that I'm doing something good and that I made someone's day by helping them with a math concept. And make sure to comment down below any suggestions or any topics you want me to cover. Thank you so much. See you in the next one, and bye-bye.